Good day, Sir Randy. We are group members Matthew, Gab, Lee, and Earl. And today we will be presenting our research on parallel integer sort, theory and practice. This study explores the limitations of traditional sorting algorithms when dealing with duplicate-heavy datasets and presents an optimized solution through a novel approach called dovetail sort.
Sorting is one of the most fundamental operations in computer science. However, traditional sorting algorithms like radix sort and sample sort face a significant inefficiency, especially when handling large volumes of duplicated data. That's why we explored the use of parallel sorting to enhance performance and scalability.
The core problem we identified is the high computational cost and efficiencies of existing algorithms in duplicate-heavy datasets. Our proposed solution is dovetail sort, which introduces a unique approach known as heavy light key separation to reduce redundancy and optimize performance.
So for the related work, to better understand our contribution, we reviewed the existing algorithms. So the parallel radix sort is efficient but falters with duplicates. Sample sort is more load balanced, but it lacks the specialized efficiency for integer sorting. So for the recent techniques like PLIS and IPS2RA also offers improvements but still face challenges with scalability and duplicates. Dovetail sorts improves upon all of this by focusing on execution time, scalability, and efficiency.
So, for the problem and algorithm, formally the problem is to sort an array A of a size and using a parallel processing while avoiding a redundant operation. We compared radix sort and dovetail sort across various metrics such as stability, efficiency, and time complexity. Next slide. So you can see here the example of the information that we have collected. Next slide. This is another one example. And next slide. And another example. So those example, dovetail sort or DT sort is our main algorithm. It separates heavy and light keys and applies target sorting strategies which minimize unnecessary work. A key innovation here is the use of parallel MSD sort in conjunction with our approach.
So, in terms of complexity, radix sorts operates at big O of n log r, whereas dovetail sort achieves big O of n and square root of log r, which shows significant theoretical efficiency. We also verified the algorithm's stability and correctness through mathematical proof and implementation.
So for the parallel MSD sort, we utilize the parallel most significant digit or the MSD sort to manage subproblems within dovetail sort. This allows the algorithm to effectively handle even high density duplicates in large datasets.
So, on the evaluation, for our experiment setup, we use a Visual Studio Code on a Ryzen 5 4600 Hz with a 16 GB RAM. We tested with 1 billion 32-bit and 64-bit integers across multiple distribution uniform. Next slide, please. Uh, the multiple distribution uniform exponential Zipfian and bit exponential. We then compared the execution time across multiple algorithms.
So, our graphical representation is a bar chart of comparing execution times of different sorting algorithm. This bar chart illustrates how dovetail sort consistently outperforms traditional methods. Notably, it shows a 6.3 times speed up on average, especially when working with datasets with a high frequency of duplicates.
That one. Okay, so recently what Miguel Francis Lee, this was the running time comparison of the graphical representation. So next is the discussing and merging step. So in terms of result, Dovetail sort showed superior performance, proving its efficiency and scalability in real-world condition. One unique feature of our implementation is the dovetail merging step, which carefully balances memory and processing time when merging sub-arrays.
So, in conclusion, or to summarize, dovetail sort significantly enhance sorting performance for duplicate-heavy datasets while maintaining a stability. Compared to radix sort, sample sort, and PLIS, it show much faster execution time and better resource utilization.
Our contributions include improving parallel processing efficiency, scalability, and optimizing sorting in high duplicate datasets, something highly relevant for big data applications.
So for the future work and recommendation, for future improvements, we recommend implementing dovetail sort on GPU architectures to increase speed further, and also adding dynamic optimization for different data characteristics and exploring memory optimization for better scalability in large-scale systems. So before we end the PowerPoint presentation or our presentation, this is our code using the Visual Studio Code. So wait, please bear with me. Okay. So we use Visual Studio Code and the Ryzen 5 from the presentation earlier and Python. So as you can see, the result, wait, that one, pivot. So this is the merge. So that's conclude our presentation. And thank you